Hello and welcome to this IOTech webcast series presentation on the subject of connectivity and interoperability between things, clouds and applications at the edge. My name is Andrew Foster. I'm the Product Director at IOTech and I'll be your host today. Today's webcast will last around 40 minutes, followed by a question and answer session. If you do have any questions that you'd like to ask, then please submit them using the QA button on the Zoom console. The presentation is being recorded and all registrants will receive a link to the recording after the webcast. Our speakers today are IOTech CTO Jim White, and for the demo sections of this webcast, James Butcher, who is IOTech's Xpert product manager. So without further delay, I will hand you over to our first speaker.
Hi again, everyone. I am Jim White, the CTO of IOTech Systems. If you joined us last month for our first webinar, welcome back. And to everyone, thank you for attending today. In case you don't know me or IOTech, IOTech is a global software company headquartered in the UK, offering a variety of IoT and edge products. While I have over 25 years in the software industry, I started my IoT edge career in Dell Technologies, where I was the initial developer, architect, and leader of a project that ultimately became EdgeX Foundry, a vendor-neutral, open-source software platform for edge computing that you'll learn more about here today. In the EdgeX Foundry open source community, managed by the Linux Foundation, I officially serve as vice chairman of its technical steering committee, while unofficially serving as the project's lead architect. Today, I'm here to talk to you about connecting things at the edge. Specifically, how do you connect sensors and devices to your back-end IT systems and applications? I'll talk you through how this is done in EdgeX Foundry, and James Butcher from my team is going to show you how it's done with a couple of nifty demos. So what is the problem we are exploring today? Putting together an IoT system, particularly an industrial IoT system, is a PhD dissertation in computer science. IoT systems deal with a complex heterogeneous collection of protocols, data models, and formats that often work across a distributed environment. In IoT edge computing, edge applications must get operational technology from the physical world to information technology centers of the digital world and back again. IoT is about coming together of the south and the north. That is, edge applications must get the south or southbound OT systems talking to the north or northbound IT systems and vice versa. This can be difficult as these two worlds don't often talk the same languages. The multitude of protocols at the southbound side make basic communications a challenge. Yet an edge application must be able to ingest the data of all sorts of sensors and devices independent of the OT technology. On the northbound side, while most things speak TCP/IP, you still have to deliver the edge data to a variety of IT applications and endpoints accepting different formats and data models. An edge platform is the interoperability middleware that must be able to deal with the complexity and the diversity of OT communications and data ingestion, and at the same time feed any cloud or other IT endpoint that turns the raw edge data into actionable information. And as we discussed in our last webinar, we believe open edge platforms backed by an ecosystem that drives an edge platform to the common good using the collective skills of many organizations, designed for interoperability and flexible, extensible enough to include other features in the future, is the best way to achieve a successful edge solution. At the heart, good open edge platforms are about connectivity and interoperability. They connect sensors and things, southbound, to cloud, enterprise, on-prem systems and applications, northbound. Then connect sensors and things to analytics packages and applications that can manufacture intelligence and make decisions that drive actuation back down to the physical environment. Once the platforms have elements of an edge world connected, they provide interoperability between those elements. They are constantly translating, transforming information and instructions from one element of an IoT world to another element of the IoT world. They translate and normalize the raw data of the OT sensor world to the applications that can use it, or another OT sensor can use. They transform, format, and otherwise organize raw data into data that can be easily ingested and used by analytics packages and decision-making applications. And they translate requests from an application into a command that a sensor or device would understand. As mentioned, the challenge of the south side is that the things, Sensors and devices speak many protocols. As examples of the depth of the challenge, some of the protocols have been around a long time, are legacy in terms of the modern IT world. Modbus was created in 1979 for use in serial communications in PLCs. BACnet has been around since 1987 and is a protocol still used in building automation to this day. Other protocols were created to take care of wireless needs. Many of these protocols, like BLE, Zigbee, Z-Wave, are used in consumer systems. And then, of course, there are traditional IT protocols that have been reused in IoT environments. Protocols such as MQTT, AMQP, for example. All of these communication protocols can be quite different from one another. Regardless of the protocol, an edge platform must connect and interoperate with the sensors and devices that speak these protocols. They must be able to get the data from the thing over the thing's protocol. They must provide a means to issue a command or actuate back to the thing using the thing's communication protocol. For a platform to be truly successful and scale to the new use cases and needs, it must also be able to address new things, new protocols quickly. Because no matter how successful an edge platform is at connecting, new devices speaking new protocols will come along all the time. Edge platforms must be able to deal with the diversity of modern to legacy protocols, acting as the Rosetta Stone between all protocols. It can't just collect data from the edge devices and sensors. It must also be able to command or actuate back down to these devices and sensors. The edge platform must be able to translate the information coming from one protocol into requests of action in another. It must allow for sensor fusion. The edge platform must understand the BACnet thermostat temperature and translate that into a Modbus command to turn off the motor lest it overheat. Don't see this as a challenge? Let's take a look at just a little bit of information about two industrial protocols to highlight the southbound challenges. On the left, information about the Modbus RTU, that is Remote Terminal Unit Communications. On the right, information about BACnet communications. Both are considered industrial protocols, so one might think they share a lot of commonality, but you'd be wrong. Modbus is a serial level protocol. That is, information is exchanged by sending data one bit at a time over a channel in one direction, usually over twisted pair wire. Information is therefore communicated in simple 16-bit message structures with start and end indicators. BACnet is more modern, and one could even say object-oriented in its communications. In BACnet communications, data is bundled into object packets that include a lot of properties and write on top of IP messages. An edge platform has to be able to provide the interoperability between these two diverse protocols and translate the messages of one to the other. On the northbound side, the issues are different, but still a challenge to interoperability and connectivity. Most of the northbound systems communicate via TCP, but that doesn't mean connectivity and interoperability are easy. Connecting to an MQTT topic is quite different than connecting to an HTTP REST endpoint, regardless of the fact that both are TCP based. At the north, interoperability is often facilitating ease of consumption. Northbound systems, be them applications, cloud systems, analytics packages, AI/ML engines, on-prem servers, are a bit picky about how they are to receive edge data. They want the data formatted in a certain way, be it JSON, XML, CSV, and they want data organized into a model structure, sometimes proprietary model structures, for easy consumption. In order to support the scale and security of edge solutions, the data may also have to be compressed, encrypted, or even filtered. Why send every bit of data to the cloud if it is not all going to be used to derive intelligence? Some northbound systems want the edge data aggregated together or enriched for additional associated contextual information, like the location of the sensor that collected the information. So at the south, edge platforms are doing a lot of translation from OT protocols. But at the north, edge platforms are typically having to do a lot of transformation. As such, they often employ a collection of independent functions to operate on the stream of sensor data they receive from the south. By the way, this technology is not new and is known as enterprise application integration or pipe and filters architecture in other realms. And while we say northbound systems, don't forget that often a northbound client is the local analytics package that is included with the Edge platform. The local analytics solution, embedded or interoperating with the Edge platform, is also picky about how it wants to receive the Edge data, just as other northbound systems are. So how do we provide good connectivity and interoperability in an Edge platform at the north and the south ends? Let's chat about how EdgeX Foundry does it. EdgeX is an open source, vendor-neutral Edge platform project run by the Linux Foundation. In fact, it is part of LF-Edge, an umbrella project for all sorts of Edge-related open source development. LF-Edge is to Edge computing what Cloud Native Computing Foundation, or CNCF, is to Kubernetes and advanced container technology. When EdgeX launched in April 2017, it started with the largest contingent of companies for any project run under the Linux Foundation to date. Today, LF-Edge is backed by more than 70 companies and affiliated organizations. It's distributed under Apache 2 license. This is the business-friendly license. Yep, it is an open source license, but the license also says you can take the EdgeX code, modify it, extend it, use it directly in commercial products, fork it and start your own open source project, or do whatever you'd like with the code without ever having to return to the community for permission or to contribute something back. Of course, the EdgeX community would hope you will join the ecosystem and contribute, but the Apache 2 license protects your rights to use EdgeX as you see fit. And the EdgeX Open Edge platform and ecosystem has industry momentum to the tune of 3 million Docker container downloads and growing at over 25% per month as an example metric of its trajectory. So yes, EdgeX has a large ecosystem behind it. And it is agnostic, running on Intel and ARM 32 and 64-bit platforms. It runs on Linux, Unix, Windows, Mac, and other operating systems. It has containers, but can also run in non-containerized environments. The community has developed Docker Compose, Kubernetes Helm charts, and Ubuntu Snaps to show flexibility in deployment and orchestration. It comes with a large array of Thing protocol connectors, including the more widely used industrial protocols like Modbus, BACnet, and OPC UA, but also provides a connector SDK for creating new Thing connectors where the open source community does not provide them. By the way, the ecosystem companies are adding value to the open platform by providing connectors where the open source project cannot in areas like proprietary protocols such as Porphyet. More on that later. It also comes with a set of cloud and enterprise connectors and example code to get data to most cloud or enterprise systems like AWS, Azure, Google, and IBM, while also providing facilities to filter, compress, encrypt, or otherwise transform the sensor data passed to the north. And of course, an SDK to create north connectors where the open source community has not provided your specific need. EdgeX microservice architecture and standard APIs allow you to easily replace elements of the Edge platform like the analytics, or provide your own extensions. Ecosystem partner companies like my own, for instance, provide connectors for time-critical applications. Further proof, the openness of EdgeX has allowed organizations to build user interfaces, threat detection systems, and other applications around or on top of the platform with relative ease. And the microservice architecture supports the ability to distribute EdgeX across whatever compute hosts are available. EdgeX was conceived to run entirely on edge gateways, but its architecture allows one part of the platform to run on the edge, while other parts run in the cloud if necessary, and supported by the use case. As we covered in our last seminar, this is the EdgeX architecture. Each box on the screen represents an EdgeX microservice. The microservices at the bottom of the screen connect to the Southbound. They are called device services, and they collect sensor data in a protocol-specific way and communicate that data to the core services in EdgeX. An SDK is provided to create device services although many you see represented in the diagram are already provided by the EdgeX community. Core data receives the sensor data provided by the device services, and that allows the sensor data to be persisted in a local database at the edge for a short period of time. This is done for two reasons. First, your edge node may not always be connected, and you must store and forward the data until connectivity is reestablished. Second, if you are doing any local analytics at the edge, your platform may need the historical data to be able to understand which way things are trending in order to make decisions. From core data, the sensor data is passed to the exporting application services, the services that connect and interoperate with the Northbound. Here, the sensor data is filtered, compressed, encrypted, or otherwise transformed for distribution to any application, on-prem or off-prem system, enterprise, or cloud system endpoint. While EdgeX provides common connectors for the cloud systems, AWS, Azure, etc., you can also create your own using the second EdgeX SDK. One application service also prepares the data for the internal use as well. Specifically, one application service shapes the sensor data to be passed to the EdgeX rules engine. The rules engine, which could be replaced with an AI/ML agent or any type of third-party edge analytics, examines the data and determines when local actuation of devices is required. If the rules engine or other local analytics capability determines actuation is required, it calls on the core command service to issue a command to the south, to the device. Device services again facilitate the actuation request on the part of the command services, translating the command request to the protocol of choice for the sensor or device. As you can see, there are a myriad of other services that provide capabilities you'd see in any other application: logging, scheduling, notification handling, etc. Each microservice is meant to do a specific job, but given its well-defined API, it can be replaced by an alternate implementation, one provided by the ecosystem, a third party, or even you. Services communicate via REST, as defined by their APIs. Some services do communicate via message protocol. EdgeX provides Docker containers along with snaps for each service, but these are optionally used. EdgeX is deployment, orchestration, and management agnostic. Here's an EdgeX real-world example use case demonstrating a range of its capabilities. In an automated factory, EdgeX allows old and new devices speaking a range of industrial protocols to connect to the platform. It then sends data to many clouds, as well as the company's on-premise applications and local databases. In place of the EdgeX rules engine, a more configurable and dynamic Node-RED engine was inserted to drive local analytics. Finally, the EdgeX solution was deployed, orchestrated, and monitored via OpenShift and Kubernetes. Although EdgeX is an open source platform, I want to mention IOTech, my company, which provides a commercial version of EdgeX called Xpert. Xpert is based on the open source effort. Each version of Xpert is based on the latest stable release of EdgeX, but adding lots of additional value. In particular, Xpert provides additional connectivity and interoperability. Along with providing commercial support with technical support guarantees, Xpert provides additional north and southbound connectors. This includes connectors for proprietary protocols like Profinet not available under EdgeX. Additionally, IOTech provides extensions and extra tools to the EdgeX platform. Extensions like XRT, which is our time-critical edge platform. XRT works in sub-milliseconds, whereas EdgeX works in soft real-time or hundreds of milliseconds. So EdgeX, or Xpert, provides edge connectivity through the south and northbound connectivity layers, each a collection of microservices. On the south, a device service provides connectivity to things that all speak a particular protocol. On the north, application services provide connectivity to a cloud system, enterprise application, or on-prem service, making the data more consumable for that north system. Interoperability comes through means of the EdgeX or Xpert core. Via the core, all sensors and devices communicate to the core and then to each other. Via the core, sensors send their data north, where the north-facing services make the data consumable to other systems and applications to include local analytics software. And because EdgeX can never provide all the connectivity in the world, there are SDKs for north and southbound service creation. Okay, so let's get a little deeper on the EdgeX southbound capability. So EdgeX device services translate the data produced by a thing into a common EdgeX data structure. If you will, the device service normalizes all data from all protocols, models, and formats into a common EdgeX model, which is part of the core of EdgeX. In the reverse way, device services take commands issued by EdgeX and translate those into protocol-specific commands. For example, a generic EdgeX shutoff command would be translated by the device service into a simple 16-bit Modbus message and sent serially to the Modbus motor PLC for actuation. The device service often talks to a sensor or device through a driver that provides the fundamental protocol-specific communications with that device. But the driver is hidden from the rest of EdgeX via the device service interface. A device service may service, that is, communicate with, one or more devices or sensors at a time. But it would do so under the same protocol. That is to say, device services speak one protocol, but potentially to a wide variety and number of devices. The device service SDKs are tools for generating the shell or the scaffolding of a device service. There are currently device service SDKs in Go and C. The SDKs do not provide a complete device service, but they do simplify the creation of the device service by providing a lot of boilerplate code that each device service must have. Device services are informed about the specifics of devices they talk to through something called a device profile. A device profile is a markup language document, specifically a YAML document, that describes the type of device or sensor and how to communicate with it via EdgeX. A device profile outlines the types of data that the sensor will send out. A device profile also describes the commands that can be issued to an actuatable device. Any device or sensor connected to EdgeX through device services must have a device profile that describes that device and what it can do and what it will report. As an example, a profile for thermostats would let EdgeX and the associated device service know that the thermostats will send temperature and humidity data as floats. It would also describe two actuation commands that can be performed on the thermostat, namely to set the heating and the cooling set points. It is through the knowledge embedded in device profiles that EdgeX has an understanding of the sensors and devices that device services communicate with. While there are SDKs to create new device services, in many cases it is hoped that you should only have to create a device profile to describe your specific sensor or device to a number of existing device services for many of the common protocols that already are connected with device services provided by EdgeX. Remember too, IOTech's Xpert comes with additional device services like Profinet, CAN, and more, not offered by the open source EdgeX. Now that you know more about southbound connectivity in EdgeX and EdgeXpert, it's time to see it in action. Here to demonstrate the southbound connectivity is my colleague James Butcher. James serves as product manager of EdgeXpert at IOTech and has helped many of our customers connect their sensors and devices of various protocols to Xpert using device services and device profiles. Take it away, James.
Hi everyone, and thanks a lot, Jim. Okay, so in our demonstration, we're going to be modelling some of the connectivity and interoperability required in a smart manufacturing plant. The use case we're going to show is about the controlled and optimised flow of materials and liquids between containers around the plant. We're going to connect up sensors on a chemical tank container from a vendor that communicates via Modbus TCP, and also a mechanised outlet valve on the tank supplied by a different vendor which is communicating using OPC UA. So the aim is to efficiently collect and bring together data from both of those devices and then normalise it into a common format so it can be aggregated and analysed. we need to be able to present that data to an operator on a dashboard in real time, be able to make decisions with that data and control each device all from the edge. And we also want to stream the data northbound to an IT or cloud system for longer term storage or detailed trend analysis maybe. So here's a simple architecture diagram of the demonstration. At the southbound side, we've got our Modbus chemical tank with Modbus registers that are storing the temperature, pressure and level in the tank, and also whether the heater is off or on. And the OPC UA outlet valve, let's just keep simple and model its state as open or closed. I'll demonstrate connecting these southbound devices to Xpert now, but later I'll demonstrate how we can connect to the northbound side as well to enable the analytics, dashboarding and cloud streaming, etc. that's been discussed earlier. So on my laptop, I'm using the Modbus PAL simulator for our chemical tank, and I've set up Modbus registers for each of our attributes. We've got simulated automations for the temperature, pressure and level in the tank. Those values will change over time, and the heater value is currently 0 because that's one we're going to set and control from within Xpert. As Jim said, in EdgeX we have device profiles that are kind of templates for each device. It's basically a config file that lists all the specific attributes a device has and how to access them. You can create those config files manually, but at IOTech we've created a specialized profile modeling tool for Xpert that makes life easier. So for example, for my chemical tank, here you define the general information about the device, so the name, a description, a manufacturer, for example. In the resources section, you define the specific attributes of the device. So here, for example, looking at the temperature, this is going to be set as Modbus holding register number 1001, and you can see that that matches up with what I've configured in the simulator. Okay, so you bring all of these attributes together in the device profile. So I have a chemical tank device profile here that you can export as a file or deploy straight into Xpert. Now I've already got Xpert running here on my laptop and already started up the Modbus and OPC UA device services. So you can see here in the Xpert Manager UI, I've already onboarded the chemical tank device against that profile. And if I click this button here, you can see the attributes that are being pulled into the platform in real time. So if I refresh this, you can see that we're tracking the temperature, pressure and level values. The heater, if you remember, was one to be controlled within Xpert. So with this icon, because it's read-write, I can set its value. So for example here, if I set the heater to be on, then you can see that reflected on the actual Modbus device. Okay, so that's demonstrated two-way data flow between Modbus device and Xpert. But I also wanted to demonstrate interoperability by bringing multiple protocols into the platform. So I'm using an OPC UA server by Process, which I'll bring in here, to represent our outlet valve. I've picked an OPC UA value here that we can model. I've picked an OPC UA variable here to be the valve's open-close setting. Again, I've made a device profile with a modeling tool, and I can connect that up into the platform by using the onboarding wizard. So OPC UA, let's call it outlet valve. We need to set the host. So the host, this simulation server is running at this address. I'll leave the security fields empty at the moment, but we do have security features. Okay, I'm going to actually use another feature of EdgeX called auto events, which means that we can automatically pull in updates from particular variables without having to keep asking for them. Okay, so I can now look at the outlet valve, which has been onboarded as a device. If I look at this control device button, you can see that the value is currently 1. Okay, so it's currently on, which matches the setting here. If I set this to another value, let's set it to 0, then it should mean that we're turning off our outlet valve or closing our outlet valve. Okay, good. Okay, so I hope you get the idea of how easy it can be to connect up different devices that speak different protocols. I'll hand back to Jim now, but I'll be back later to show connecting up at the northbound side and using the data at the edge. Back to you, Jim.
Thanks, James. So we've spent some time describing and showing you EdgeX Southbound connectivity and interoperability. How about the Northbound? As already described, application services take EdgeX data and make it available to northbound systems, which include cloud systems, enterprise applications, analytics engines, third-party systems, etc. Application services will also filter the data as you see fit so that the other systems and applications get only the sensor data they need. Filtering can be done on the basis of originating device, for example, only data coming from a thermostat, or the type of data, only export temperature data as an example. In general, application services allow you to specify how the information EdgeX has collected is to be transformed for better consumption at the north. As a simple example, maybe the thermostat data collected is in Fahrenheit, and the application you want to send the sensor data to expects temperature data to be in Celsius format. Application services will typically send data via HTTP or MQTT, but could be customized to really communicate via any protocol you desire. Application services, as mentioned previously, contain a collection of functions. Functions are connected to one another such that output from one function is the input of the next function, which we call a pipeline of functions. An application service sends the data received from the sensor through each of the functions of the service until it comes to the last function, which sends the data to your designated endpoint, which again could be an HTTP REST address or an MQTT topic, to name a few examples. There are application service functions to format the sensor data to JSON or XML. There are functions to filter the sensor data as mentioned to send only what is relevant to the receiver. There are functions to compress the sensor data package before sending it out, and there are functions to encrypt the sensor data. An SDK is provided to create new application services, just as an SDK is provided to create southbound device services. The application services SDK contains a number of pre-built functions to use in your application service, but you can also create your own custom functions. The SDK provides general scaffolding code to make creating a new service easier and faster. Lastly, there's an already created application service called the Configurable application service. This service requires no programming to use. It comes with a number of pre-built functions that you can choose to use or ignore. You define which of the functions you want to use through configuration versus programming. The Configurable application service also comes with several examples of how to configure it to do some common northbound connectivity, such as connect EdgeX to Azure IoT or Amazon IoT at the north. The Configurable application service provides a quicker means to connect EdgeX to a number of enterprise and cloud northbound systems, but without the flexibility that a custom application service would provide. Let's not forget that application services also get EdgeX data prepared for consumption by analytics packages. Today, EdgeX ships with a Drools rules engine as its analytics capability. Drools is a Java-based rules engine built largely for enterprise environments. As with all of EdgeX, there's flexibility to interoperate with an alternate solution, that is an alternate analytics package in this case. The application services can provide data for your alternate choice of local analytics system and get the EdgeX sensor data to that system. As an example, IOTech has sensor data routed to a Node-RED engine versus Drools by default. We prefer Node-RED size and scriptability a bit more than Drools. Through its microservice design and flexibility, EdgeX can interoperate with and use almost any analytics capability. Okay, as usual, I've talked long enough and it's time to bring back my friend James to demonstrate the northbound connectivity and interoperability. Take it away, James.
Okay, thanks. So a quick check back on the architectural diagram for the demo. And we've connected our different devices to the platform, but now we want to use that data in order to make some insightful decisions at the edge and deliver the data to various applications that might need to do some control and so on. So Edge Xpert has built-in application exports to a number of different formats. The first example I'm going to show is InfluxDB, which is a time series database for the edge. Influx works very well with Grafana, which is an open source dashboarding tool that lets you really see what's happening in your system. So I've already created and enabled an export to Influx, as you can see here, and I'm asked for all of the data from Xpert to be streamed into it. And by the way, you can filter and limit the specific data that you want to stream. In this tab, I've got a Grafana dashboard set up. So you can see the first row here is the Modbus chemical tank information. So the heater is currently on, the level and temperature and pressure values are set like this. You can produce graphs and tables and so on to really give you insight into what's happening. I'm also presenting the OPCUA outlet valve data, and that's currently closed. Okay, not much is happening there. Now, if we want to make some decisions with the edge data or run some automatic rules over it, we might choose to use Node-RED, which is another open source service we distribute with Xpert. As Jim mentioned, Node-RED is a flows engine that lets you write simple logic rules to make decisions over the data. Node-RED has built-in nodes for MQTT and REST. They're both supported by Xpert, so that fits pretty well with the platform. I've already got this simple flow created here that connects an MQTT source and performs some logic and sends some control commands back to the devices. In this case, when any of the key values get above a certain level, we're going to open the outlet valve. So we're going to set the setting value to 1 and then pass that to the next node, which is the REST command to set the outlet valve setting. That rule is already running, and I can deploy that. I just need to create an export to MQTT so the data starts flowing into Node-RED. Now, back in the manager, I already created the export, but it's currently disabled. So I can go in and enable that like this. These are the values, I'll keep them the same. I only need to send the chemical tank data up, so I'll filter on that. And now if we go back to Grafana, we should see that whenever any of the settings get above this red line, we should see that the outlet valve is opened, and obviously the chemical will flow out of the tank. So yeah, you can see that here. The valve is opened because both of those settings are above the threshold level. Okay, so we should see, yeah, the rules kicked in. As the levels drop back down, we'll close the valve and so on. Okay, good. So that's decision making at the edge. And by the way, IOTech has enhanced each of the device services to be smart device services. That is, we've added capability to do filtering, transformations, and inject pluggable user functions into the device services while they're running, which means that we could easily write a rule where the Modbus device service could have its heater automatically turned down when the temperature of the container reaches a key point, for example. Doing that in the device service, that is, before the data has even been sent up into the core layers of EdgeX, is a really good optimization that means decisions can be dynamically plugged in and made with really low latency. And finally, I wanted to show connectivity to a cloud platform. I've chosen AWS in this case, but the platform also supports Microsoft Azure, Google, IBM, and many others. I've already got the export established to AWS, but again, it's currently disabled. So if I go into this wizard, I can enable it. You can see the settings I applied, the address of my thing in Amazon, the MQTT topic I'm using, can I call it chemical tank, and then my certificates and keys. Okay, I just need to send the device, the chemical tank device filter information. And then in my AWS IoT tab, I can see that I've got a shadow set up for my chemical tank, and you can see that now Xpert is exporting that data up into Amazon, and you can see that that tracks the temperature and pressure levels right at the edge on our Modbus device. You can start and stop the different cloud integrations as you go, so your edge platform doesn't tie you into a single vendor. Okay, good. I hope all of that makes sense and shows the different range of connectors that we can support with the platform. With SDKs at both the southbound and northbound side, more connectors can be easily created as well. Okay, thanks. Bye for now. Back to you, Jim.
Thanks, James. We hope you've enjoyed today's webinar. In the session today, you learned about how the open source, vendor-neutral edge platform of EdgeX Foundry supports edge connectivity and interoperability. You saw how EdgeX allows you to connect various things speaking any protocol at the south side, as well as making sensor data readily consumable for any cloud or enterprise system at the north side. You saw how EdgeX, with its layers of connectivity microservices, provide the interoperability glue that brings the OT and IT worlds together. You saw how EdgeX device services translate sense data from things to a common EdgeX data structure, and how application services take that sense data and prepare it for an external application or system to include an analytics package. You also learned about IOTech's Edge Xpert. Built from EdgeX, it's a commercially supported implementation of EdgeX for business-critical deployments. Xpert provides an extensive range of configurable southbound and northbound connectivity options out of the box and not always available with open source EdgeX. In addition, IOTech's graphical tools make the process of onboarding new devices and sensors a simpler process that can be performed by an OT engineer. Please join us monthly as we provide you more information in our quest to help you understand and solve IoT and edge computing problems. And if you want to learn more, please contact me at the email address you see on the screen or visit IOTech's website, iotechsys.com. By the way, the video recording of the talk today will be made available to you. Look for information on how to access it coming to your email box shortly. Thanks to James for his great demos, and thanks for attending this webinar.